Hi, I'm Massimo Bartoletti from the University of Cagliari and I will present a joint work with Stefano Lande and Roberto Zunino. This talk is about using Bitcoin to execute smart contracts. Actually, Bitcoin already supports smart contracts, but in a very limited form. In particular, Bitcoin does not support custom tokens that are one of the most successful use cases in other blockchain platforms. For instance, in Ethereum, token transfers involve approximately 50% of transactions. Past attempts to implement custom tokens on Bitcoin used the blockchain only to record token transfers, but they needed an off-chain central authority to enforce their security. Actually, the Bitcoin script language is not expressive enough to check that the token is not double spent or that different tokens are not joined together. As a consequence, it was not possible to use these tokens within smart contracts, like for instance decentralized token exchanges. Recently, there have been proposals to extend Bitcoin with covenants, a script operator that allows a transaction to constrain how it can be spent by a child transaction. This form of covenant makes it possible to implement non-fungible tokens in a secure and efficient way. Indeed, we show in this paper that this form of covenants gives rise to a model of smart contracts that is Turing complete. Therefore, at least in principle, one could use these covenants also to implement fungible tokens. The problem is that such an implementation would be extremely expensive and inefficient. Intuitively, one would have to simulate a counter machine. In this paper, we introduce a new kind of covenant that allows a transaction to inspect not only its child, but also the whole neighborhood, including its parents and siblings. Building upon these covenants, we show how to implement fungible tokens efficiently and securely. In the rest of the talk, I will give a few insights on our construction of fungible tokens. The building block for smart contracts in Bitcoin is the transaction. A transaction can have many inputs and many outputs. The inputs specify which transaction outputs the current transaction wants to spend. Each output has two fields: the script that must be satisfied by a transaction that wants to redeem it, and the value of bitcoins that will be transferred. The script language only has arithmetic and logical operators, hash, and signature verification, on the redeeming transaction only. Notably, transactions can only transfer bitcoins, while custom tokens simply do not exist. The extension of Bitcoin with covenants allows transactions to have custom fields and introduces the script operator berrec. Here I am requiring that the script in T0 must be identical to the script in the redeeming transaction. Recursively, this guarantees that all the transactions along the chain will have the same script. It is easy to implement non-fungible tokens with these covenants. Symbolically, we model the behavior of non-fungible tokens as a transition system, where the states contain transaction outputs. Here, we start from a state where Alice has n bitcoins, which she uses to mint 1 unit of token foocoin. The only possible action on non-fungible tokens is the transfer. Here Alice transfers her foocoin to Bob. It is not possible to split a non-fungible token into smaller units. At the Bitcoin level, minting a token is rendered as publishing a transaction like T0. The transaction has a custom field to declare the token owner. The script ensures that the redeeming transaction is signed by the current owner. The covenant ensures that the script is preserved along the chain of transactions. By spending T0 with T1, Alice is transferring the token to Bob. Fungible tokens support more operations besides minting and transfers. First, we can split the token units in a transaction between two transactions. Two transactions holding the same token can be joined into a single one. Further, two users can exchange their tokens at a desired rate. At the Bitcoin level, implementing fungible tokens requires two additional fields to record the performed operation and the token balance. The script is a switch among the various operations. We will use covenants to preserve the script along the chain of transactions. The token transfer is similar to the non-fungible case. The only difference is that here we also need to check that the token balance is preserved. We can split the token balance in a transaction by spending it with a transaction with two outputs. The script must check that the sum of the token balances equals the balance in the spent transaction, that the redeeming transaction has exactly two outputs, and that both of them preserve the script. We can join two transactions by spending them with a single transaction. Here, to preserve the token balance, the script of T1 would have to check that the token balance in T2 equals the sum of the token balances in T0 and T1. To do that, the script of T1 would have to inspect that of T0 and vice versa. Further, T1 would have to check that T0 has the same script and vice versa. Now, this is not possible using standard covenants, since they can only inspect the children of a transaction. To overcome this issue, we extend covenants with operators to inspect the sibling transactions. In this way, we can implement the needed checks in T1 and T0. For instance, here we require that the token balance in the redeeming transaction, T2, equals the sum of the balances in the two siblings. This implementation, however, is susceptible to attacks. For instance, assume that Alice has minted foo token and that Mallory has minted another token, adv token. Mallory can join 8 units of foo token with 7 units of adv token, obtaining a transaction with 15 units of foo tokens. This is clearly wrong. The problem is that even if the two transactions have exactly the same script, the script cannot discriminate between different tokens. To prevent the attack, we add another transaction field, which records the token identifier, and we use covenants to preserve the identifier along the chain. In this way, the attack we have seen before is no longer possible. Indeed, since T3 is trying to join foo tokens, then the script in T2 will fail, because the token identifiers in T2 and T3 are different. However, the script is not secure yet. In another attack, Mallory could mint tokens with exactly the same identifier, foo token, and then join them to the foo tokens minted by Alice. Note that forging tokens of any type is always possible, since the custom fields in the mint transactions are free. To prevent this attack, we further extend covenants to allow the script to also inspect the parent transaction. We then check that the identifier in the mint transaction equals the hash of its parent. In this way, Mallory could still publish a transaction to mint foo tokens, but this transaction is unspendable because the new condition is violated. Our main result is a computational soundness theorem, which states that any execution of tokens at the Bitcoin level has a corresponding execution at the symbolic level. This guarantees that the implementation respects the specification. If attacks were possible at the Bitcoin level, then they would also be observable at the symbolic level. To conclude, We have proposed a Bitcoin extension that makes it possible to construct secure and efficient fungible tokens in Bitcoin. Compared to the existing proposals, our neighborhood covenants can inspect the parent and siblings of transactions, besides their children. This extension can be implemented efficiently by suitably caching data in Bitcoin nodes. For instance, caching scripts would allow to implement the VREC operation as a comparison between two hashes. Finally, we note that programming contracts on Bitcoin with covenants is rather complex and error-prone. A consequential research question is how to design high-level languages for Bitcoin contracts, also supporting security analysis techniques. Our previous work on BitML addresses this question for pure Bitcoin, but the extension with neighborhood covenants makes the problems much more interesting.